Okay, great. Good afternoon, everyone. Thanks for showing up. Wow, and quite a few numbers too, so it's great to see this type of attendance. I'm going to be talking about the 2020 network, which is, I felt it was far enough ahead in the future that I wouldn't be held accountable for it, and hopefully none of you will. So the first thing I thought would be useful to take a look at is, what do we do? When we break down to the essentials of what infrastructure OEMs do is, I basically trade in three different things. I'm moving data, I compute on data, and I store data. And it's, these simple objects that when combined create very complex systems. What I found is that over the course of about 20, 30 years or so, is when two of these basic building blocks start to combine, when we get convergence in them, we start getting some fairly destructive value creation that happens in the industry. So it disrupts profit pools. And I think we've seen three already. And these are strange things, because when you start talking about them in simple terms, I think you start to rationalize how big these changes are. And it's these weird, moments when, I think, when you dwell in them, you realize it's kind of like, when you first discover that, bad things can happen to good people, or that, over arbitrary timescales, Keanu Reeves is making more money than I am. When you see those things happen to you, you start to realize that we're in the middle of a new one right now, and that it's going to disrupt everything that we've seen before in the past. And I want to talk about where we are now, but before that, let me build up to it. So the first one is, I think, symbolic or emblematic of this particular slogan that came out of Sun Microsystems way back in the early 80s. It was John Gage who kind of coined this term, the network is the computer. And effectively what happened is that compute and network met together, and they converged, and they created really a new paradigm, a new model for how network is going to work. The second big convergence was when the data and the network converged. This is when file systems came out, SAN started to become a little bit more prolific, and it entered into this network storage era. I think this was obviously something where it created the rise of a whole new set of industries. Companies like EMC started to come to the fore, and indeed are still very strong forces today in the industry. So where are we now? We're in the middle of what I'll call the compute and data convergence. Now there's a lot of different things that can happen, but I think this is modeled off of things like Hadoop. I think more, in the narrower term, it's being influenced by technologies like Spark. The idea here is that, I can do big data type analyses on data that's actually stored in remote storage, and what you have is basically latency between that remote storage and the compute, or I can just kind of put them one on top of one another and start computing in real time against it. So I think what we're seeing is this move away from basic Hadoop file storage systems, where it's very, very batch oriented and has a significant amount of delay associated with it, to something more like Spark, where you can create more of a combination of stream-based analytics on top of data that gives you quite a bit more speed in terms of the time to get to a particular outcome, which is important, obviously, when you start to take a look at analytics as a means to trigger workflows within a network. So that's where we're going. How is all this stuff combining to create a new future for us? I think the terms that you see are things like the industrial internet, the second economy, a new digital supply chain. All of these things are building upon the shoulders of all these different convergence events. And I want to talk a little bit about how fundamentally this has changed the environment in which infrastructure OEMs and service providers are existing. So I think where we're heading is this reality where we're trying to make some of the distributed philosophies that application developers have kind of embraced. We're making those fallacies true. And if any of you are familiar with Peter Deutsch, another Sun Microsystems alumni, I'm picking Sun Microsystems so they don't exist anymore, so I can actually make reference to them without having to worry about it. Peter Deutsch actually identifies as a music composer today, but in his time he was an amazing advocate of distributed compute technologies. This is really what happens when you take network complexity that engineers who kind of trade in selling infrastructure. When we build things, they're very complex. And when an application developer takes that, he doesn't actually recognize a lot of the complexity that hits behind it. And these 8 fallacies that you see here are things like there's zero latency in the network, that everything's homogeneous, that one policy in one administrative zone is homogeneous with another policy in another administrative zone, that there's zero cost in transport. All these things are, I think, fallacies that some application developers hold true. And once you actually are able to break the barrier between these fallacies in your application, you can get some pretty differentiated applications. But what we would like to do is abstract all that complexity that embraces these fallacies and allow application developers to have their cake, to make those things homogeneous, to make the underlying network look like it's zero cost at the end of the day. And I think this is what you'll find is the general trend when we start to develop abstractions and we start coining these terms like software-defined everything. It's related to making these fallacies true. So the idea is, let's go into the engineering toolkit. Let's abstract for simplicity. This notion of cloud technologies, SDN and NFV, are all rooted in this basic principle that I'm going to take the complexity of the network and abstract it so that it's really easy, that I increase the accessibility of the network, and therefore I should create some network effects as a result of being able to do that. When you make things more accessible, more people use them, more people use and consume them, it makes the network more valuable. And obviously this is something that has a lot of fear for infrastructure OEMs, in particular engineers who make all of their money in trading in complexity. So it does require a different philosophy as we move through it, and we're finding that those philosophies are starting to bloom, and I think starting to take some shape. So why do we need to do all that? We've gone through these convergence events. We're starting to apply software disciplines to our network, and the question is, why are we doing all that? So there's two truths. There's two reasons I think that are driving this reality. The first is that I think the basis of competition in our industry is shifting. It's moving away from the scale and robustness of a few network services like voice, messaging, and data access to the choice and flexibility of many, many different applications. And I think this is a picture that helps to reveal or underline that. When you take a look at something as simple as voice, we're seeing a pretty prolific explosion, a Cambrian explosion, if you will, of different services based on the key DNA of voice. This whole notion of every session of a voice service has been innovated by different companies like Skype and Twilio and others who have taken that basic service, are working with telecom APIs in some cases, in other cases not, but they're developing some fairly innovative services. They're moving away from one device to any application to any application. They're moving from a business model where the voice is actually monetizing the network, where those two things are decoupled. And when you do that, you start to see different types of business ecosystems that can emerge. And these are prevailing ecosystems that I think are starting to win the race in terms of what the end state is going to look like. When I take a look at just simple messaging apps, if you take a look at WeChat from Tencent, they're going to average somewhere around a little over $1 billion this year. 85% of that is going to come from gaming. So gaming off of a messaging platform doesn't seem real, but what they've actually done is built in internet payment systems inside that messaging app, and as a result, they're actually able to do some pretty compelling things. In some cases, you'll see small enclaves selling fruit through that, or smartphones. In other areas, are actually selling virtual goods. But the model is no longer just one of I'm going to monetize through advertising or monetize the audience. They're actually getting into the realm of m-commerce, and I think that becomes pretty interesting when you think of how these things are going to exist and be monetized. Advertising is really a limited pool. There's about 200 billion or so of revenue that's available globally, and if you go to m-commerce, that's $1 trillion industry. So obviously something that's a little bit more of a profit pool for them to take advantage of. I think the second big thing is the result of all these various technologies are driving us to a dollar ARPU economy. And I don't mean to say that everything's going to be $1, but certainly I think that that's a fundamental limit that we're trying to hit. And I think it's largely dictated by the application economy. If you take a look at some statistics from iFlurry here, they're showing that the average cost is starting to trend somewhere around 50 cents. I think $1 is probably from a median perspective what we tend to expect from an app store type experience. But I do think that as you move to choice and flexibility of applications from just a few services, that the trend line in terms of what the ARPU is going to look like is more like $1. So you combine that vision in terms of how the basis of competition shifts, and we have to move to basically a return on the capital that an operator invests into their equipment so that they can actually be profitable at $1 per transaction per month. So, the other reality of getting into an era where you're defined by the shift in competition is that we start to have to put in much more flexible and less risk-washed infrastructure in order to experiment more. You don't really have this case where you can take the past 150 years of voice and forecast forward in terms of what the penetration is going to look like, and therefore start issuing what type of voice licensing schemes you need to be enjoying over the next 10, 20 years. It's very different. These are economies that don't necessarily have a tremendous amount of history. So to forecast out, you have to basically reinvent the business model. And to do that, you need to have scale experimentation. And there's a lot of different things that have to happen, but effectively you start to substitute your revenue and you look at these new areas that you're trying to substitute that revenue for, and you don't really have a great base in terms of what that growth potential is going to look like. So what you have to do is start to adopt the types of techniques that are prevalent, I think, in economies like Google and Amazon, where they run massive multivariate analyses on A/B type schemes. So at any given time, you're actually not running the Google or the Amazon, but you're running a version of it. And when you're actually going through that, you're able to start to create what are the conditions that make this particular application successful. So you're inventing on the fly, in many cases, what that customer experience is. We don't really have the mechanisms to be able to rapidly do that in telecom infrastructure. And this is where we need to get to as you move towards this explosion of new applications, to be able to understand what is actually going to create a delightful experience to the end user. You need to start taking a look at this. I think the second big driving force is what's happening in internet architecture and the economics in particular of internet architecture. This is this 2005 picture, just kind of blank out the 2013 one, but the 2005 picture, this is from a textbook that my nephew showed to me because he's in a computer science course, and I looked at it, I flipped to this, it's right near the spine, and I was just horrified. He said, "That's what the internet looks like, Uncle Vish." And I'm looking at this going, that's exactly not what the internet looks like. A lot of people think that's what the internet looks like. And indeed, if you drew this back in your computer science days, you would have a national backbone carrier. There was about 10 to 12 of them back 10, 15 years ago. They took all the costs in the internet, but they also took all the value. They were settlement free amongst themselves, but they actually charged everybody lower in the layer a transit or peering fee in order to carry the traffic. So you had NAPs, you had regional access providers, you had local access providers who provided the commercial networks, and they took the subscription fees from the consumers, and so money kind of flowed up, traffic flowed down. That's not what the internet looks like anymore. Around 2006 or so, there was probably somewhere around 1,500 different sources of internet traffic that kind of combine to create the data gravity of the internet. If you go to something like 2010, there was probably about 150 different AS domains that constituted half of the internet traffic. So massive compression in terms of where traffic comes from. And then if you take a look at what happened in 2013, it was the top 50 ASs that combined to form 50% of the internet traffic. And then you flashed to this year, in May, it's the top 30 ASs that combine to form the top 50% of internet traffic. So a tremendous amount of compression, and what's happening is a couple of things. One is there's consolidation happening in the industry, and you've got companies like Google buying YouTube, companies like Yahoo buying Flickr, so there's consolidation of where data is coming from. But you actually have three other things that are pretty important. One is that you've got a lot of centralized internet exchange points. And so companies like Terramark, which is acquired by Verizon, companies like Equinix, which have high peering capacity inside their footprint. You've also got tremendous concentration because of CDN providers. Companies like Akamai, LimeWire, Level 3, they constitute the great volume of traffic that's coming through. And then you've got cloud companies. You've got companies like Amazon. You've got companies like Rackspace, who have created a large data center footprint. And what's happening because of that is that you've got this new peer layer inside the internet. And that peer layer is creating data gravity in terms of where the data is sourced and where the revenue is coming from. I think as a result of these large data centers that you see in the backbone of our internet, what's also happened is that the interconnect has become much more dense. In fact, you're seeing a lot of these big players, whether it's Amazon or whether it's Google or others, they're pairing directly with the access networks and disintermediating, in some cases, the larger transit providers. And so because of that, because you've got data centers now, which is creating kind of the rhythm and the heartbeat of the internet, this notion of creating much more software-defined structures, which has really been the philosophy of a lot of these data centers, becomes much more relevant in terms of how to actually steer and govern traffic inside the internet. So where does the end game of the network need to be? I was at Whole Foods the other day, and I was trying to convince myself, why is this experience so great when I go to Whole Foods? Because I'm sitting there, there's these great farm-to-table type experiences that you get, where I can buy onions from a farm outside of McKinney, and I can buy some grade A beef that was farmed maybe within 50 miles from my house, and I'm paying this huge premium and have a smile on my face. Why should I be so happy to fork over all my money? And yet, at the end of the month, I feel so horrified at getting my utility bill or my telephone bill or anything like that. Why is it that that is a horrifying experience and this is a great experience? And I think to an extent it's because I've got choice. When I go there, I'm not paying a bulk fee for everything that I get at the supermarket. I'm paying a different fee for different individual produces that I'm buying. So to me, if the network can become something like that, where the network actually has defined services that I consume in a transactional way, that to me might be a much more delightful experience. Can I get a CDN in the moment when I need to deliver video traffic, when I'm on the fly, and I want the CDN that performs best over a mobile infrastructure? Because I happen to be using, my cellular connectivity or my Wi-Fi connectivity. Can I get an on-demand VPN and have that provisioned in seconds versus 3 months? These are the types of things that, to me, constitute more of a marketplace for the network, and can we drive towards that as an end game? And the question is what is holding us back? So if I take a look at those drivers in terms of convergence, in terms of moving towards something that has a basis of competition governed around choice and flexibility of applications, that I have something that respects where the internet architecture and economics are coming from, what are the things that are holding us back from taking those and creating more of a marketplace within a network? And I think there's 5 basic things that I look at. One of them is compute, second is operations and observability, the third is storage, the fourth is network, and the last is mobility. So I want to talk quickly about each of these. So on the compute side, as you start to host things inside of a data center, you've got this issue where you want to have a homogeneous environment, but every workload is a snowflake, and you want to be able to optimize for that particular workload. And there's a couple of different types of compute architectures that you can apply, and what we're trying to move from in terms of a challenge to the infrastructure OEMs is from the share everything architecture, where everything's in a closed circuit, where your storage and your memory is in a closed circuit with my processing elements, to something that looks more share nothing, where everything is partitioned in terms of my CPU, my memory, and my storage. And this is actually a pretty difficult transition because we've got applications that are highly stateful that actually are much more guided by the telco principle as we see today. As you move to something that's share nothing and it's stateless, you have a very different type of design philosophy in terms of how that application is going to be instrumented and deployed on top of that. The middle is kind of that halfway point, and this is where enterprises are today, was kind of more of a shared disk infrastructure. And these are great architectures, obviously a little bit more resilient, but it has a single point of failure. It gives you some of the abilities to do distributed compute across the processing elements, but you can reduce a lot of the complexity which comes through the storage side by having shared access. In terms of unit economics, if that's 1, if you look at the share nothing, that's like 0.06. So there's a pretty dramatic difference in terms of cost to be able to realize your applications in a share nothing environment. However, it comes with a tremendous amount of complexity in terms of how you engineer your application. So the second thing is, as you move towards these software architectures and you move towards these abstractions, you actually start to create a lot of complexity. And the number one question that I get at the tail end of being an infrastructure OEM, we sell stuff to operators, especially if it gets to me, because that means it's a really, really hard problem, is why isn't it working, right? The 3 big things is why isn't it working, why isn't it working, why isn't it working? And you have to be able to answer that, right? So, today there's the blame wheel, that typically goes through, and you can resolve the blame wheel. That's what you see here, where you have a problem that might be in the database, and the database vendor says, no, it's the operating system, it's the kernel. And the operating system says, no, it's back at the application, and it goes around, and you really have a hard time creating accountability in that structure. Now you can resolve it. There are tools, especially in something where you just have a physical one-to-one mapping of things. But imagine now, if now I have a logical to physical mapping, and now everything's become really, really complicated. So how do I prove what the problem is and what it isn't, and how do I measure the magnitude of the problem? That's where you want to get to. And so creating observability within that network is massively important, because things like latency are just going to become even more and more important as you move forward. And latency is obscured, especially when you have a layer of software between it and you. So this is going to become very important at every layer of the software stack, moving from system calls, moving from process calls into the kernel, into each of the VMs in terms of how you profile them. All that's going to be important for us to be able to get a consolidated profiled view. People rapidly say that the issue here is because it's the malformed SQL query. So storage. Storage is difficult. It always sounded easy, and certainly when I started off in the industry, this was a really easy concept: storage. You just store stuff in rows and in columns within a particular memory structure. But now you've got all sorts of different things. Now you've got things that are base or ACID. And ACID is kind of the old relational database system that everything's very, very consistent, everything's atomic, and then you've got base type structures where everything's eventually consistent. And obviously you kind of want both depending on what you're doing inside your data center. And so this creates a lot of complexity because you have different systems that are being governed. You've got something like HBase, and you've got something like an Oracle RAC system, and those things don't necessarily have a consistent way of governing them. And so the question is there an easier way where I can get a database system that can respond to both? That'd be the holy grail, and certainly that would be something that would merit kind of mention in this network of 2020. It turns out that if you actually put a time calibration across your storage systems, which is actually kind of funny because I started off in PDH type systems where there was timing distribution and sonnet systems, and everybody said, that's ridiculous, don't use sonnet, use this asynchronous thing like IP. And of course we started ripping out timing distribution, and when you find that timing is actually something that's critical for being able to get that balance in storage systems, it just makes me laugh and say, I told you so. But anyway, there's a different concept that's coming out with Google's Spanner system, where they are time serializing events. When you time serialize events in a database, you can actually get the best of both worlds. And the error in that is really just, if I can reduce that error to really, 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 really low figures, I can create high transaction volumes that can be either ACID or base against a system. So pretty revolutionary things that are coming back, and I think plays on the strengths of what we've engineered these many years in telecom. So network. What are the big changes in network? To me, the number one question always comes up is bandwidth versus optimization, quality of service versus throwing more capacity at the problem. And the holy grail for me, which is never actually manifested, is I've worked on every quality of service system that exists. Right? I worked in ATM, I worked in DSCP, IntServe, DiffServe, you name it, I was on it, and no one's ever deployed it. Certainly there's some deployment, but it's not deployed in the way certainly that we wanted it to be deployed, because it turned out you could always throw more capacity at the problem and you didn't need quality of service. And there was issues with what we really wanted to do with all those QoS mechanisms, which was to be able to do traffic engineering, which actually is really important. If you can do traffic engineering, that would be cool, but you could never do traffic engineering in a distributed system, because distributed systems only give you partial views of the network, and it's a suboptimal problem. You really want something that's more centralized. And so as you take a look at some of the concepts that are coming out with SDN as a for instance, where you can actually create a centralized map abstraction of your network, you can start applying some engineering techniques to be able to optimize traffic flow across your network. I think this is a pretty interesting capability, and I think it's also one of the values of SDN which people don't talk about enough. Because most people talk about replacing routing protocols, which I actually think is probably the wrong thing to focus on. Don't replace routing protocols. Those are the things that we do well. Let's try to do stuff that we actually don't do well, which turns out to be things like traffic engineering. Now, this shows you the SWAN network from Microsoft, but Google did this in their before network, where they took a look at the average utilization on their inter-data center links, and they found it sits at like 34% because they're not engineering the traffic correctly. Now, if you actually can get a centralized view and then make thoughtful decisions about where to place traffic in an optimized way, you could start to reduce or increase rather utilization to somewhere around 90%. So that's a massively useful tool in the toolkit. I think the second thing about this whole notion of moving towards a network where I can manage the resources more effectively, comes down to things like NFV, which I think is going to be really the enshrined technology at the center of SDN. And if you take a look at what's happening inside NFV, you've got the NFV infrastructure, which is largely all about the compute and the data center. You've got the NFV appliance itself, which I think is really just creating information models of appliances that we already have and putting them in virtual environments so that I can place them wherever I need. But the third is the area where I think is becoming really interesting, and it's becoming the more complicated part of it, which is the orchestration and management part. And I mean both. You need to be able to find and place and create a service, and then you need to manage the life cycle of that service. And I think that new intelligence that we're putting in place can't just be limited to one protocol like OpenFlow, which is, I think, where you hear all the sexiness of SDN. It's got to include all of the legacy networks, all the physical network functions that exist. And I think when you take more of a top-down look at SDN and you consider the fact that I can have different networking protocols, I can have management protocols, that I can have NetConf as well as SNMP, as well as things like forces, as well as things like BGP, FlowSpec, manipulating the data flows and doing PBR-like functionality in my network. I think that's where you start to get a better picture of what the possibility for SDN is going to look like. So mobility. The issue here is we want to be able to have any endpoint, not just human endpoints, but thing endpoints. And we want to be able to work with any type of workload and any type of device, whether that device is a sensor or other. And I think as you go through that, it really creates a new complexity in your network. Because when I started off doing mobile networks, engineering cell edge was all about getting 8 kilobits per second so that I can keep that voice service up. But now you take a look at it, you have to have coverage for different types of services. It needs to be a messaging service. It needs to be a data service or a video service. And those things increase the complexity of how you manage your network. And I think this is going to be one of those things that will create a different way of building network management systems. It's not going to be experience management from the perspective of the network out. It's going to be from the application in. And I think as we start to look at that and we use that as a metric for basically being able to create, hopefully a useful user experience in terms of who's using Facebook or who's consuming that Netflix video, that we're going to be able to do that with the tools that we put in place and the resource management that comes with something that's more software defined. I think the last reflection here is that while I think this notion of creating new types of experiences for applications is very much a today issue, tomorrow we need to start taking a look at what are the new technologies that are coming through. And I'll nervously call this 5G, but we don't really know what 5G is. But we do know what are some of the governing technologies. We do know that we can get into these massive MIMO type situations where if I can have more transmit infrastructure versus the receive infrastructure in the terminals, you can start getting a proportional reduction in the power that you need at a cell site, which is actually going to be very useful. But if I can also do that, I can start creating more spatial channels and be able to multiplex those to get higher and higher data rates. Also very important for the people who want the headline view of 5G, which is all about capacity. I think very dense deployments is going to be really interesting because now you can do interference coordination in a different way, especially if you have more antennas at the terminal. So I think this is going to be super important as we move towards a system that has many more transmitters and many more receivers. New waveforms are going to be important. By that I mean millimeter wave type applications. Not just dwelling in the sub 2 gigahertz, sub 3 gigahertz, where you're going to get some amount of increase in the available bandwidth that's required to deploy these networks. You need order magnitude increases, and to do that we need to work in millimeter wave, which have tremendous issues in terms of propagation effects, because that's largely dictated by the frequency. There are ways to do that. If you have large antenna arrays, you can keep the antenna aperture constant over those frequency-dependent paths and actually use things like millimeter wave technologies efficiently. It will require different types of random access technologies because they're going to be much more directional, but it is possible. And so I think as we move towards state-of-the-art, this is going to be something that's going to be, I think, a large headline topic. Spectrum access, whether I do full duplex operation, meaning I have transmit and receive in the same breath, whether I go to spectrum sharing type regimes, like what's being considered at 3.5, I think all these are going to be fundamental changes in terms of how we build and use our cellular networks. I think the last one here is really this notion of beyond the cellular construct. We're still based around a unit of construction that talks about a cell, right? And that's been a long, long time, since the early days of Bell Labs, since Ring Young's first paper was all about let's base it on the cell. But there's new types of ways of implementing cell structures. If you look at distributed antenna systems, which is kind of the first iteration of that, you can go further and say, well, why don't I split my signaling control traffic from the actual data traffic? Let's split that up. Let's make it independent. Let's actually have a difference between where I got my uplink and my downlink, so that I get phantom cell structures that sit and float through the network. I think these things are going to create the next level of spectral efficiency in our system, and are going to be pretty large design changes in terms of how we manage and build our networks. So all that to be said, when you combine all these things, I think we're coming to a fundamental new abstraction. In fact, the only abstraction that I think makes sense moving forward, which is a world of things. Mobility is our backplane, and cloud is the destination. If you're not building for this abstraction, I think you're losing out. I think we're moving very quickly towards this. 2020-ish is what I put, but obviously it could be further along. I don't want to be that precise about it. But to me, this is the end game that the industry is moving towards. This is really what the network of the future is going to look like. And so with that, let me close my presentation, and thank you very much for your attention today.